Okay, so we've just played with the simulator, and you've seen Charles' law, Boyle's law, Guy-Lussac's law. In fact, we didn't really do Guy-Lussac's law, but we could, right? Hold the, what does Guy-Lussac hold constant? The volume constant, and then see how that changes the pressure and temperature, okay? But I put in 2 pumps, and then we play with gas. Actually, let's just talk about that gas, or the gravity for a second. So I'm going to put in a couple pumps of gas here. I'm going to hold nothing constant, and I'm just going to let everything kind of go to wherever it would naturally go. Now this is how we always think of a gas in a chamber, right? Going everywhere, filling its sides of the container, no problem. But do we have 0 gravity on Earth? No, we've got some gravity on Earth, right? So technically it's more like this. And to make it a bit more extreme, we would say, okay, there. And so do gases actually fill the sides of their container in real life? Not really. They almost do because our gravity, we don't have lots of gravity. We have a medium-sized gravity. But you can see how it's more dense down here than it is up here, right? So in real life, gases don't exist like they ideally, like we think they ideally do. Okay? But as scientists, we have to start talking about an ideal gas. So I'm just going to talk to you a little bit about an ideal gas. And in your package, at the very bottom of this package, on that page here, you'll see some bullet points about what an ideal gas is. So now by ideal, I mean idealistic. Okay? Not realistic, but rather idealistic. And we have to have this idealistic gas in order for us to say, hey, look, it's a perfect relationship. As I perfectly double the pressure, the volume will perfectly halve. Perfectly. Okay? Which doesn't actually ring true if I think about stuff like gravity or whatever. So I have to say that there are no forces. So do you see that in there? There are no forces in those 3 bullet points or whatever there are about an ideal gas. No forces that interact on a gas. So no gravity, but also, let's just pretend this is nitrogen. So if I have nitrogen, that's one circle, and I have nitrogen, that's another circle. What's happening in between those 2 nitrogens from our bonding unit? That is a force. Come on, you guys. Force of attraction between these 2 nitrogen molecules. Dawson. Close. Intermolecular force. Specifically which one? London dispersion forces. Does it have dipole-dipole? Does it have hydrogen bonding? No, so only London dispersion forces. So most of you, when you were walking around the room yesterday, and this was our balloon, the room was our balloon, and you were pushing and putting pressure against the sides of the container, right? You were traveling in a straight line, weren't you? Except for Ben. Ben was attracted to the idea of bumping into his friends. So everybody was going straight line, straight line, straight line. Hit the sides of the container, bounce exactly back, straight line, straight line, straight line. Agree? You were an ideal gas. Ben was more like a real gas. Because some gases are still the gases, all gases, are slightly attracted to the other gas. So they do, as they pass by each other, kind of wane towards each other, because like 2 magnets passing, there is a slight attraction in their straight line. So gases traveling in a straight line is quite idealistic. Realistically, they're kind of ooh, as they pass another molecule, they'll sort of weave as their intermolecular forces are attracted as they go past. Does that make sense? They don't stick together because they're moving, right? They are, whoa, this one isn't moving anymore. Huh, it is too cold. Let's talk about that, actually. So, because I don't want to fix it and then fix it back again. So these molecules, as they're going past each other, I'll change that in a second, you should see ideal gas, straight line, no interaction. No interaction with gravity either. So there's no forces that affect them. They travel in perfect straight lines. That's idyllic, not realistic. Okay? But here's another one. 0 Kelvin, and this is still a gas? Are you kidding me? I haven't reached its melting point yet, or its freezing point, we say. 0 Kelvin, do you think it's still going to be a gas, or do you think at some point the gas will have condensed to a liquid, and the liquid will then condense to a solid, and at 0 Kelvin it should be a solid? In fact, if I just squish this volume a little bit, I get, oh, blew the lid.
Pump some more.
Reset. 1, 2, close this, cool this.
No, it's cool. All you gotta do it so slow, right?
So I'm cooling it, I'm cooling it. I'm cooling it, I'm cooling it. It's now at 0 degrees Celsius, right? And I'm cooling it, I'm cooling it. I'm now at negative 100 degrees Celsius. Are you telling me this gas hasn't yet become a liquid yet, right? And condensed? That would just be ridiculous. Of course it has. But an ideal gas does it. In order for us to look at the properties as it changes, in order for us to, Xander? Screen. Not that screen, this screen.
I don't know the phone.
Okay, good. In order for us to play with these ideas and think what would happen when I reach 0, what would happen to the gas, it has to stay as a gas. So ideal gas is no forces like gravity or intermolecular forces, but also it doesn't condense. No melting point, no boiling point, doesn't condense into a liquid, which is just ridiculous. It should, right? You don't think you need to jot these down to engage with the material and become more part of the subject? Absolutely, boys. Pick up your pens. Okay. So it doesn't condense. It has no attraction. When you guys were making your balloon, and I was saying you're getting colder and colder, and the balloon's volume is decreasing and decreasing, right? And you huddled around over by my desk, and you became 0 Kelvin. And therefore we said 0 volume, right? And 0, absolute 0. Were you really 0 volume? No, in fact, I even called you, pretend your size is insignificant. Well, remember Xander. So I said, you are insignificant right now. Because actually, you fill a balloon with marbles. Those marbles don't have to be moving, and that balloon will still hold a shape, right? You guys were molecules. You are circles. Having the circles in that balloon should mean the balloon should have some shape, some volume, because the circles are there. So we have to pretend that gases in our ideal world have no shape, no size, no matter, insignificant. Okay, so that's the other point on there. It says particles have 0 size. So why can't I get this to become, when I make this 0 Kelvin, why doesn't this kind of disappear? Well, because these circles still have a size. But if we're imagining our ideal gas that would have 0 size, they could condense into nothing and have 0 volume. Do you understand that concept? Nod your head or shake it. Yes?
If it has 0 size, how does it create pressure?
It doesn't at 0 degrees Celsius.
Yes.
Oh, you mean the pressure of the thing? It still has a force. That's what I mean about it being an ideal gas, not a realistic one.
Yeah, but like what would be moving? Like what would hit the pressure meter?
The thing that has no size. The force, the wind, the sun, energy, right? Energy, not matter.
Yeah.
Okay? And again, not realistic, idealistic. Okay, yes?
So is that like kind of how like aerosol cans work? Like you increase the pressure so it turns into a gas, and then like when you release it, it turns back into a liquid?
Correct. Correct. And propane tanks, because propane's a liquid at room temperature, it's the same thing. Yeah. Okay, is there anything else that you need to know about an ideal gas? Not really. So how do I get a gas, if I'm doing an experiment, a real experiment, how do I get it to become as idyllic as possible? Well, I have you guys traveling as fast as you can. So Ben doesn't have a chance to go, ooh, hey, right? You're just going in a straight line, fast, 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 fast. So the faster these are moving, the less interaction they have with each other. Would you agree with that? How do we get them to go fast?
Increase the temperature.
Increase the temperature, okay, so let's do that. Let's increase the temperature, so now I'm becoming an ideal, closer to an ideal gas. Oh, let's go reset. 1, oh, wait a minute. What do I do about the size? For an ideal gas?
There's 0.
0 size. So should I use my heavy species or my light species? The light species. So I'm going to reset again, go back to my light species because they have a much smaller size. Right? Did we do this together? Did we do light species already? Yeah, okay. So light species and high temperature. What else makes it an ideal gas?
Condense.
They don't condense. Well, if it's a high temperature, it's not condensing. So that's good. It'll stay as a gas for sure. And there are no forces. Well, I can't really take that away other than pretend it has 0 gravity. But like I can't take the intermolecular forces away. But if they're going faster, like temperature is high, then they have less time to alter their course. Right? The slower you are, the easier it is to swoop. Right? If you're traveling fast, it's pretty hard to deviate from that fast path, from that straight path. Okay? Any questions on that, what an ideal gas is? Okay, so, and also on that package is the kinetic molecular theory. The kinetic molecular theory is something that you were introduced to like in elementary school, so it's just here again, and it's saying that all matter is composed of particles. Oh, yeah, okay. There are spaces between the particles. Do you agree? Yeah, Xander, you're following along with your book. And the particles are in constant motion. Okay, and there are forces of attraction between these particles, which we go into detail about in Chem 20, the intermolecular forces. Okay, so kinetic theory, ideal gas. Got it? Okay, so I want to look at one more thing today, and it's this. I'm going to go back to the heavy gas just because we can see the circles a little bit better. And we're just going to go back to the normal temperature, so 300 Kelvin. So this is about 30 degrees Celsius. And let's just see what the pressure becomes, 1.3 it should. 1.3 and a little bit atmospheres. Okay? All right. We have not changed the number of moles in our flask. Agreed? Every single time we've said, hey, here's my flask. Here's the first situation. What would happen if I change the volume? Now my second situation. Right? Here's my first situation. What would happen if I change the pressure? A second situation. Let's just talk about this situation right here. 300, 1.3, I'm going to put 1.35 because it keeps fluctuating, and a volume of that big. What would happen if I add more moles of gas to this situation?
Everything goes up.
Everything goes up? Everything? Let's talk about one thing. Let's talk about pressure. So if I increase the number of moles of gas, what do you think should happen to the pressure? It should increase. As long as what? The container stays the same size, the volume stays the same size. Okay, so let's just try that. Oops, just a second. Equals an increase in pressure if the volume is constant. Gosh, this sounds a little bit like when we were doing Boyles and Charles and stuff, right? One thing constant, looking at how one thing affects the other. So here we go. Increase. I'll pump it twice. More. And is that guy going to stay there? He is. And the pressure indeed did increase, with the volume staying the same and the temperature staying the same. Everybody okay with that? All right. Can I put an equal sign? What do I say about the relationship between number of moles and pressure? They're directly proportional. Remember, like volume. Boyle's law said that volume and pressure, one increase, the other increase, they were, oh, pardon me, I don't mean Boyle's law, I mean Charles's law. One increase, the other increase, directly proportional. Gay-Lussac's law, same thing, directly proportional. Everybody okay with that? So what should we, how could we look at the volume then? Number of moles and volume, how they're related. What do we need to hold constant, do you think? So I'm going to pump in some more moles. I'd like to know how it affects the volume.
Well, won't it depend on like what kind of container you're using?
This is a flexible container.
So it could expand then,
It could expand. Why would it expand?
because there's more pressure.
Right, so it's going to try to bring the pressure down. So we're going to hold the pressure constant and temperature, by the way. Okay, so let's hold the pressure constant. And let's hold the temperature constant, which it'll do for us anyway. And I'm going to pump it twice. And you see the guy expanding in order to get that pressure. I forgot to write down the new pressure. I can't remember what it was to begin with. Anybody notice? It was 3 point something, and it's 3 point something still. Okay, so to maintain the pressure, it has to push the volume out. Okay? So if the pressure and temperature are constant, what happened, and I increase the number of moles, what happened to the volume? Thank you, Wes. What happened to the volume? Number of moles increased, what happened to the volume? Increase the volume. So what do I say about these two? They're related? Directly proportional, like this. Okay? What about temperature? So I need to hold what two things constant now? Volume and pressure. And I need to then figure out what happens to the temperature. Right? So, in order to get this volume to go back into that space, right? I want to squish this volume. It's not going to let me. I need to cool it down, right? Cool it down a little bit, and then that guy will move for me. Stop. Yeah! Okay, so what happened? I had to decrease the temperature in order to accommodate for those extra moles. So if I increase the mole, what happened to the temperature? It had to decrease. What do we call that relationship? Inversely proportional. And how do I write that? A proportional sign, 1 over T. See that? Have you written it all down? So combining these three ideas then, what do I end up with? Well, my number of moles is proportional to pressure. It's also proportional to volume, and it's inversely proportional to temperature. Oh gosh, PV over T. Have you seen that before?
Yep.
Oh, the combined gas law. P1V1 over T1 equals P2V2 over T2. Right? I probably need to write it here. P1V1 over T1 equals P2V2 over T2. See? They're the same. And I can't put an equal sign here because it doesn't equal my number of moles yet. But it does vary by a constant. That constant is called the ideal gas constant. And it is 8.31. So as long as I multiply 8.31 by my number of moles, I can equal my PV divided by T. You see that? Now this formula is most memorized by rearranging it. Oops, the camera's not quite getting that. If I multiply both sides by T, I end up with TRN equals PV. Everybody get how I got the blue? And then they flip it. So they say PV equals nRT. And students tend to memorize it by saying perv nerd. Okay? So
Senior class change.
you'll hear chemists, you'll hear chemistry students calling this perv nerd. But it is actually the ideal gas law, or pardon me, the combined gas law, equaling the number of moles times an R constant. See how they're related to each other, first of all. Do you see that? How all those experiments led us to this. Now the great thing about this blue formula that's different from the green formula was always changing. I have a balloon, it has a pressure, a volume, and a temperature. I squish the volume into a smaller volume. What's the new pressure, right? Do you always have to be squishing your balloons? Or increasing the temperature in your balloon to change your balloon. No, actually sometimes I just have a balloon and I want to know what its pressure is. Or I want to know what number of moles are in there. And so that's where this blue formula comes in handy. I have a balloon. It has a pressure, it has a volume. I would like to know what the temperature is. Does that make sense? So this is for just one situation, and this is for a changing situation. So if you're reading the question and it talks about a change, I have to use that one. If you're reading the question and it just talks about one thing not changing, then I have to use the blue one. Okay? That is the last bit of theory, the last formula that has to do with this unit. So this formula helps you answer questions 7 through to the end on that ideal gas, what was it called? Gas laws assorted problems. Okay, so now you can answer all of that sheet. Tomorrow I'm still aiming to do an experiment.